Formula sheet suggestions. First of all, a lot of this chapter is the antiderivative of f of x dx. Of f of x dx. And you get big f of x. What's missing?
dx.
No, the dx is there. This is part of the notation, antiderivative of f of x dx.
Oh, parentheses?
The bracket.
No, we don't need bracket.
The interval.
You're thinking of the definite interval. Plus c.
Oh, no.
Right?
Oh, no.
Don't forget that constant of integration when you're doing the antiderivative. And then let's talk about how you do this on the TI-89. What's the command? I hope you had a chance to go there. I brought some extras.
You go into calculus or
Second in calculus, it's right on your front screen.
Second and 7.
Yeah. It looks just like this. Second and 7, right? Second and 7. Second, 7. Left parentheses. Now you can either enter in, if you have y1 of x in your calculus somewhere, that's great, or you just enter in the function, right? But you need something else. Count x. It's almost exactly like what you have here. Now watch out though. Watch out. The TI-89 forgets the plus c. You've got to remember that. When it does an antiderivative, it doesn't try to list all the general solution. It gets just one of the solutions. Okay. Now, contrast that with this. This is called an antiderivative. Also known as the indefinite integral. Indefinite integral. A good chunk of the chapter, though, is definite integrals, where you have limits of integration. Definite integrals. The integral from a to b of f of x dx. That's where you use the brackets. Big F of x evaluated from a to b, which means big F of b minus big F of a. You don't do the constant integration because they cancel out. They subtract from each other. We'll use some more examples of that today too. Okay? How about on the TI-89 for this one? It's the same symbol, right? Got to start with the function, y1 of x. Now, I'm putting y1 of x there because that's if you want to look at the function. While you're looking at it in your y equals menu and your graphing menu, you can also then refer to it then on your home screen. Comma, x, comma, a, comma, b. Okay? So this is all legal stuff you could have on your formula sheet. If you forget what the sequence is on the calculator. But notice, the definite integral is a little trickier. But again, you're putting in all the information you see in the symbology. You're putting in the y and the dx's. So you got to say what variable you're taking the integral with respect to. Okay? Now, let's go through some integral tricks. These are other formulas you can have on your sheet. Okay? The most basic integral is integral of dx. What does this d stand for? Derivative. And this is antiderivative, or the integral. So you just get x.
Plus c.
Plus c. Oh, okay. There you go. So what if you have the integral of k dx, where k is a constant?
Oh, okay. It's kx.
It's just kx.
Plus c.
Plus c. Because the constant multiplier can come out outside. So the integral of k times f of x dx you can say is k times the integral of f of x dx. Notice I don't put a plus c there because I haven't done the antiderivative yet. Okay? Those are some handy little tricky rules there, right? Now the big rule. Ready? The big rule. X to the n dx.
Equals,
What does this mean? Crank it up.
X plus 1 divided by
Crank it up 1 power
over n plus 1.
over n.
over n plus 1.
Plus c.
Plus c. Go! Okay.
Man.
Now watch it though. Hold it. Hold it. There's a fine codicil on this one. Where?
There's a what?
N cannot equal -1.
Oh, yeah.
N cannot equal -1, or you got that. So how do you do the integral of dx over x? That's what some of your groups are going to do under law derivatives. Works out to be a very easy formula. But it's not covered in this group. Okay? Alright, I think that's all our integral formulas. One thing to be careful of, though, is this whole idea of if this is u instead. Like the integral of u to the n du. It's still u to the n plus 1 over n plus 1 plus c. But sometimes u might be some function of x. So look for that. Do you have something inside a power or square root where you've got its derivative beside it? And this is the closest thing we have. We'll talk later. Did you sign in?
No, should I?
I'll just mark you late.
That's what I thought.
Okay. U equals f of x. This is the closest thing we have to a chain rule. It's the chain rule in reverse. You can't distribute antiderivatives over multiplication or division or anything like that. And there is no quotient or product rule. But at least you have this. And we'll see some examples. Oh, that reminds me over here. Can we do this? Integral of f of x plus g of x dx. What do you get there? F of x dx plus g of x dx. You can distribute the antiderivative addition. So, when you've got multiplications and you don't see one of these patterns, you're going to have to consider just multiplying all out. And then you can take the antiderivative of each of the terms. And this works for addition, subtraction too, of course, right? Integral of f of x minus g of x dx, that would be the integral of f of x minus dx minus the integral of g of x dx. Okay, a few more suggestions for the formula sheet. And then we'll start looking at the examples. Integral from a to a of f of x dx.
0.
0, that's that tricky one, right? Because it's the area of the curve, right? If you only go from, if your left and right bound are the same line, you just have line segments, so it's 0. Integral from a to b of f of x dx plus the integral from b to c of f of x dx. Notice you have the same integrand, the same thing inside the integral, and there's this connection between the limits of integration. If that's the case now, we can put it together into one integral. But what are the new limits? A to C. A to C. So you've got to have this connecting. The upper limit on this one has to match the lower limit on this one. Then you can put the two areas together and they have one big area. Okay. Integral from a to b of f of x. Is that the same thing as the integral from b to a of f of x dx?
No, it's negative.
It's the exact opposite, so don't forget that. The exact opposite. Okay? Then there's one other concept. The integral from negative a to a of f of x dx. Well, that's from A to A. It'll equal 0 if f is odd. Right? Because the area under the axis is going to be negative. If the points go below the axis, that's negative area. It cancels out the positive area above the axis. But that'll happen in odd functions because you have this kind of pattern. Right? The integral from negative a to a of g of x dx equals, if g is even, though,
It's going to be 2 times the integral of 0 to a dx.
there you go. There's no canceling part. Now it's even. So you're going to have the same areas on both sides, so you could just find the area 1. You might say, well, how's that going to save me? Well, I think a lot of you have seen the frustration you get when you have to put this lower limit in and subtract it. If the lower limit is 0, it's a lot easier to do the arithmetic. Okay. So that's it for formulas. Okay.
What about the definite integral and thing? It's like
Oh, right.
f of b minus f.
Right. The mean value theorem for integrals, and specifically, let's just focus on the average value of a function. Okay? Thank you for bringing that up. The average value of a function. Average value of a function that is equal to the integral from a to b of f of x dx. Basically, that's the area under the curve. And you divide by what? B minus a. B minus a. You divide by the width. So you take the area of that big chunk of graph, divide it by its width, and that will give you the average height. Average value equals the average y value. That's kind of implied. Somebody just wrote that it's not average value of the x. No, the average value is referring to the average y value of an integral. That's that ice sculpture thing we did. Where you melt it down. If you melted it down, it kept the same width inside the bucket. And what would that height be when you refroze it? That would be the average value. And the mean, hello! This one. Yes? Yes, now I just read only all of a sudden. Uh-oh. You know what that means? Oh, that's so clever. That's okay, we just go this one. See? Is this the one we didn't work on yet? Right. That's okay. Hey, we go like this. Not to worry, friends.
I'm not worrying.
We'll save it as something else. 6 review notes for the cool class. What is this, group?
Just cool class.
Group. Cool class.
With a K. Cool class with a K.
No. Okay. Great. All right, I think that's all our formulas. So let's look at some of these. Note, you can't just crank this up and crank this up. You've got to expand it out. Okay? And what I thought we'd do is I'd just do a survey of all the things, and then we can go back and do more examples than ones you're not quite getting. Okay? What I did with this document now, that's accessible, this review notes, it has both of the practice things on there. Some of you have the hard copy with you. Some of you looked at the video. That's actually an earlier test from before that. And so the test might be like either one or some sort of new permutation of it. Notice, if I give you the integral, I expect you to do it by hand. You can certainly check it on your TI9. And here's the TI9 choking again, not giving the plus C. Okay, so be careful of that. Do you see how after we expand it out, now you can take the antiderivative of each part? And reduce the fractions. In this case, there's no reducing, but if it was 3x cubed over 3x, we can reduce that. Notice on this one, foiling it out helps first, and then you crank it up, like we did in the other one. It is not necessary for you to get it into one fraction. So don't worry about that. Don't forget your constant integration, though.
Do we have to do the factoring thing that Webson makes us do? Is there like...
No, you don't have to have the final answer factored. That was handy when you did derivatives, because often you set the derivative equals 0. We're not going to end up setting the integral equal to 0. Okay, here number 2. Now this one's a little different. It seems to be the same thing, except you're giving extra information, which basically is getting you to a specific solution. If you just do the antiderivative of both sides, and notice I like doing this thing where I move the dx over here, so yeah, I took the derivative of y with respect to x to get this. Now I have to take the antiderivative, so I like to separate the variables and do that. But that's not necessary. As long as you show me you're taking the antiderivative of both sides, and you start taking the antiderivative, this is 3x squared minus 1. Don't forget the minus 1 actually becomes an x. Plus the constant, that's the general solution. Now you can put in 0, 2 to come up with that constant. Okay? This next example is like, now this is all available to you, right? Online? Okay. As a PDF. And now it's going to be a video as well. Okay. In this next one, you have 4x minus 3, 1 comma 5. So again, we have to take the antiderivative, gives us a general solution. We get the specific solution by putting in that 1 point. This goes back to what you did in Algebra 1. Remember, if you were trying to find the equation line, if all I told you was the slope, you'd go, well, there's a lot of lines with a slope of 3. Then I say, oh, it goes to the point 1, 2. Now you can use point slope to come up with the equation. So same thing here. Giving you the derivative is telling you the slope. That's not enough to actually determine which of the many functions that have that thing as its derivative. So this narrows it down to get the specific solution. Okay, this is like the moon problem you did in WebAssign. Notice working backwards here. You take the antiderivative acceleration to get to velocity, antiderivative velocity to get to height or displacement. So this was the first step. And notice I put a thing in here now. Now sometimes what I'll do is I'll throw an extra little line here like, okay, fine, you've got the velocity and displacement equations, but can you apply them? So that's what this is about. Determine the maximum height the ball reaches. So in this case, that maximum height is going to occur when, well here, this is just getting this and this, the velocity and the height. And when is the height at its maximum? You can either say it's going to be when the velocity is 0, and that happens at 198 seconds, and then you can plug that in. Or you can look at the max of this height graph and set again a velocity equal to 0. In either case, you get this 198ths. And you got to plug that in to actually get the maximum height. This problem's a little different with the Planet Claire. You drop from a 64-foot tower. It's dropped, so the initial velocity is 0. This one I probably went a little overboard last year. I'm not going to get everything as complicated. It's just that, unfortunately, some kids assume to be proportional. That since Planet Claire has half the gravitational acceleration of Earth, they assume that it would take twice as long, and it doesn't.
Planet Claire like the B-52 something?
Is there a different Planet Claire?
If we use a physics formula instead of going through the calculus way, will be downgraded?
Yes. Yeah. It's nice to have those handy, right? Especially if you remember some of those. And you can jot them down on your formula sheet if you want to use it as a check.
Right.
But yeah, I want to see you go through basically solving a differential equation, backing up from acceleration. Okay. And here's, now this one definitely says do it by hand. And you can check the answer with the calculator. Okay, cranking it up. There's the TI-9 check. There's another one done by hand. I think we'll practice doing some of those. Watch out for these problems. Sometimes I've had kids leave this whole thing blank because they say, well, I don't know what f of x is. I'm not going to do anything with this one. Ouch. You want to start with a 90? Work right down there, okay. But come on, look at the given information. You're not given what f of x is, but you are given all these definite integrals. And some combination of those definite integrals will help. And here's a nice twist. What if I said the integral from 0 to 3 of f of x plus 9er dx? What? Nobody said anything about 9. We'll call this,
Why do you put a 9?
we'll call this f flange. No, I'm saying if this was another question. Another question. How are you going to deal with this?
You take the integral of f of x and then add 9.
Are you going to add 9? Does a constant adder just come on outside? No, constant multipliers can float outside the integral symbol, right? But in addition like this, we have to think of this as the integral from 0 to 3 of f of x dx plus the integral from 0 to 3 of 9 dx. Which is just 9x. See, so you didn't need to know the formula. If it's a constant, if it's just a constant inside the integrand, then it's just going to be 9x evaluated from 0 to 3, or 27 for that. What do you get for the integral from 0 to 3 of f of x dx?
10.
That's 10. So 10 plus 27 equals 37. Okay.
Can you add any number? Does it have to be like 9, or can you have like 5? I'm still confused why you added 9 as the constant.
No, I created a new problem, f.
Oh.
Yeah, just totally new problem because there's a lot of variations on this. Notice the trick here, since the limits were the same, it was 0. Right. 0 to 6 of f of x, it's a good thing we had 0 to 3 and 3 to 6, so that could get split up. Okay, so you got examples of those. Now here, set up the definite integral, then use geometric formulas. This is where I'm not going to let you, even though you set up the integral, you have to show me how you're coming up with this area by using geometry. So, you should add that to our list of formulas, okay? What are the key geometry formulas that you keep seeing?
Based on height.
I think pretty good. And there's also a trapezoid formula, right? So let's just go back to the beginning and look at, yeah, right here. Yeah, let's add in one more. Something you can include in your area sheets. Area formulas. Area of a rectangle, of course, base times height. Area of the triangle, 1/2 base times height. What about a trapezoid? A trapezoid like this.
The average of the
We have a base and maybe you have 2 heights. Average of
the bases.
right, so well, there's 2 ways to view it. You could view this as here's base 1 and here's base 2 and here's the height. Or you could have a base and have 2 different heights. So you could say either the average of the bases times the height, or the average of the heights times the bases. Okay? It's basically turning the trapezoid back into a rectangle. And last thing, of course, area of the circle. R squared. There you go. R squared. All right. Now we can get back to that section we're looking at. Did we do? We're up to this one, looking at. There's a couple problems involving set up the integral to find the area of the curve, right? Now, don't get the wrong impression. There's just 10 questions. I just put together 2 practice tests on here, okay? So you get more examples of each. So, first of all, I'll give you the function and I'll give you the picture. Now you have to describe that with an integral. So you go from 0 to 5, you go along the x-axis. Dx. Now, here it looks like I split it up into, I had to figure out what that intercept was. Maybe when the slope that line there. Just need to do the areas. Yeah, triangle plus the rectangle, 8 plus 4 equals 12. Or you can do the trapezoid trick, average height times the base. Do it in one step. This one's a couple of trapezoids. You could also use that, since it's even, that doubling trick. Now, if you set this definite integral to find the area, set that represents the area of the region below. I forgot to put the region below on there. I think it's on the next one right here. Yeah, 0 to 3. Now, I do say integrate to a value, but in this case, you could go ahead and use your calculator. If you're setting up the integral, you may use your calculator to find the integral. Unless I specifically say otherwise, like I did in the last problem where I wanted you to show me the geometry. Now, this one it says integrate by hand, so following the directions, you're going to integrate by hand, and that's right in the next step. But like for these average value problems, the average value is the integral divided by the base, the b minus a. So if you set this up, you could do this on your calculator. Because it can do quite a lot of work. That's that ice block I was talking about. It's like we're melting this big curvy thing down to a rectangle. Now, the mean value theorem for integrals just says that you have to attain that average somewhere in the interval. So you can just set that into the value and find it. Okay? Now, these last two involve identifying an inner function. And so I do want to practice some of those. So that's what your final. This one is an indefinite integral, so you can have a plus c at the end. But watch out, if we let u equal x cubed plus 3, then du is 3x squared dx. And so you happen to have handy there the du. 3x squared dx is right there, so replace that with du. So it becomes the integral of u to the half du. And so you can crank up the power. But there's no subtracting, there's no valuing from a to b since it's an indefinite integral. But make sure you unsubstitute. Your final answer should be in terms of x. Notice on the definite integral, though, this is another indefinite integral. On the definite integral problem, I put limits of integration on there, and I change it from, it's x cubed plus 3, so I write that as u is x cubed plus 3, du is 3x squared dx, so I need a 3 in there. I change this to 1/3 integral from 1 to 2 of u cubed du. And notice what happened to the limits of integration. These change using this chart, using the idea that u equals x cubed plus 1. And by changing the limits of integration now, I can just find the exact definite integral by keeping it in u's. I don't have to change it back to x's. So be careful of that. When you're changing and doing substitution, you don't just put a u in here and keep going. You got to make sure that you have du available and so forth. And of course, that one on the practice test was just monstrous, but not so bad if you recognize that this whole thing, if you call that u, du is the thing hanging beside there. So it just becomes u to the 5th, u to the 4th. Why does that say 1 to -5? Oh, because I had to figure out what the new u was, right? X is going from 0 to 1, so u goes from 1 to -5. This is one where you would have to do it by hand, but you can check it in your calculator. Okay, which ones do you want to practice? Some more of them. And again, we'll probably practice the same cool class document will be available in the other classes. So let's see if we add any more examples in the other classes. Nine. Let me make up another one like 9. You're hoping I'm just going to remember the one I wrote this morning. No, I don't think so. if I did that? So 9 is just an indefinite integral. Integral, let's say the antiderivative of dx over the cube root of x squared plus, no, x cubed plus 3x plus 9. Now, notice I'm going to put something up here, though. I'm going to put an x squared plus x. X squared plus x dx over cube root of x cubed plus 3x plus 9. Okay, is that tricksy enough for you? Yeah. I'm going to make one more adjustment, though. Shh! X squared plus 1. Yeah, okay. What do you do?
Make the bottom like A.
The whole bottom?
No, you make x cubed plus 3.
What's inside the cube root?
Yeah.
Okay. So, let all that equal, I think our standards rise are rather u. Okay. U equals x cubed plus 3x plus 9. So what's du?
Oh, 3x squared plus 3.
Dx, right? Now, here's the problem. We don't have that handy. Instead, what we have, see this before going. We got this thing. Cha. I'm going to lose all those extra lines. You don't quite have du. You have to prep this. Multiply by 3. So where did you get that 3? Just showed up for you?
Yeah, you can put in and take out constant multipliers.
Well, where'd that 3 come from?
Oh, well, when you multiply the top by 3, then you're going to get to that du.
Well, yeah, you want it to be there, but if you just suddenly ordered up a 3?
Yeah, you can put in and take out constant multipliers.
Okay, that's right. Where's your compensation for it? You can't
Oh,
solve
you got the 1/3 on the outside, sorry.
You get to put a 1/3 out here, okay?
That's right.
Notice if I didn't put this x squared or any kind of x's in here, we'd be stuck on this problem because basically you don't have the derivative of the inner function here. So for right now, your tricky antiderivatives integrals are based on the fact that it's something like what somebody did after a chain rule. They have the derivative of the inner function handy as a fact. So that's what you have to do here. So now you can say it's 1/3 antiderivative of, now the whole top is du. And the bottom is the cube root of u. So see that whole idea here? All of this, that's du. You gotta make sure you have du in there so you can see. Okay? Now, that's 1/3 antiderivative of, how do you take an integral of this thing? Yeah, right as a power of u now in the numerator. U to the negative 1/3 du. Because the cube root is 1/3 power, it's at the bottom, so it's at negative 1/3 power. So now you can crank it up. U to the negative 1/3 plus 1 over negative 1/3 plus 1. Plus the constant of integration. Now here's where that 3 can come in handy. Because the 1/3 times, right? This is 1/3 times. The 3 can distribute through here. You got negative 1 plus 3, or 2 on the bottom. So you have u to the 2/3 over 2 plus c. Still not done though, friends.
Now you substitute back in.
Yeah, unsubstitute. So you have x cubed plus 3x plus 9 to the 2/3 all over 2 plus c. And you can leave it like that. You don't have to make it into a radical. Now your calculator might make it a radical. Generally found it doesn't. You can just do it. Go and check it out. Okay, what else? Let's find the area of this. Let's do an area problem. Well, let's do an average value problem. That would be, yeah, number 8 here. Hey, find the average value from average value of f of x equals square root of 9 minus x squared from 0 to 3. What? Find the average value of f of x equals square root of 9 minus x squared from 0 to 3. So that's going to be the integral from 0 to 3 of square root of 9 minus x squared dx, all divided by what? 3 minus 0, or 3. Now this is where you get stuck though, because we don't have, you can't do this by hand. Because if you let u equal 9 minus x squared, d would be minus 2x. You could sneak the negative 2 in, but not the x. You can't put an x here and a 1 over x out there. That's a variable. Only constant multipliers can move outside. So what do you do? Remember what I said before? If you set the integral, unless I say otherwise, you can just do it on your calculator. So let's do it on the calculator. What do you get? What's the TI-9 say? Integral square root left parentheses 9 minus x raised to the 2 right parentheses comma. It's a raised to x going from 0 to 3.
3 pi over 4.
You get 3 pi over 4. Now you're dividing the whole thing by 3, so you just get
No, that's divided by 3.
okay. So it's 9 pi over 4 for the integral, and then you divide by 3 and you get 3 pi over 4. What? I don't think that's right. Oh, no, it's right. It's right. Because where's this pi coming from? What kind of shape is this? Y equals the square root of 9 minus x squared. Y squared equals 9 minus x squared. X squared plus y squared equals 9. You've got a circle. In this case, a semicircle is just the top half. And you're shading in this corner like this from 0 to 3. So you could have also done 1/4, because it's a quarter circle, pi times the radius, which is 3 squared. That's 9 pi over 4. That's another way you could have come up with this. Okay? Alright. So, know when to use your calculator. I'm going to let you use the calculator, because it says otherwise. And I think the only exception is that one problem where I didn't want you to do the definite, the area of the curve. I want you to show me the geometry. But all the other times, if you set the integral, like an average value problem, or an area problem, you can use your calculator to find the definite integral. Generally, though, you do have to know how to do an antiderivative by hand. The calculator's there to help you, and you can check it that way. Okay? All right. Say it with me now, people. Okay. Flange out.